Welcome everyone to a video on programming artificial life. Some of you may be wondering what is meant by artificial life. Maybe you imagine something like this. But this isn't really what I want to be talking about today. I mostly want to be talking about a concept called soft life or software life, a set of mathematical programs and simulations whose resulting outputs mimic in some way life itself.
Select tutorial.
More specifically, today I'll be teaching you how to program particle life in Python, something akin to what you see on the screen right now. This tutorial won't be a comprehensive tutorial of the latest and greatest methods for the fastest possible simulation. That is not the point. The point is to show people with very little programming experience how to make particle life in Python. There are definitely better ways to do it, better programming languages, and better methods. But hopefully by following this guide, it gives you a firm enough understanding of how to program particle life so that you can build on it yourself. Maybe even port it to another language or just play around, see what you can find. Also, most importantly, this is just my way of doing it. Really, there are as many ways of doing it as there are particles in particle life. Alright, now that I've mostly covered my ass from the criticism of 10x programmers with 20,000 years of experience, let's start. Generally, when I'm programming, the first thing I want to be able to do is analyze what I'm actually programming. In this case, I'd quite like to be able to see the particles in motion so that I can confirm the behavior is, well, correct or lifelike. So I start with importing CV2 for image rendering and NumPy, then defining the X and Y sizes of our CV2 window, creating that window with a NumPy array, and then showing that window. Ah yes, the deep dark void. As much as I'd like to stay here, we must move on to create life. I think the next good step is maybe drawing some particles on the screen. But first I set some CV2 properties to ensure that I always get a full screen. Next I generate the particle's XY position randomly within the boundaries of the screen. And finally, inside a for loop, we loop through every particle and draw it as a circle on the screen. Et voila, the closest thing to Starry Night any of us programmers will ever make. Next, I think it'd be nice if the particles could move, and if I had different types of particles. Just so you know, there's some variety. So in the code I set up the number of particles I want, and a delta time for the movement. I then create a dictionary containing all the colors I want. This could be done programmatically, but for now I'm hard coding the colors. Next, I give all the particles a random type. This will tell me what color that particle should be, and eventually how it interacts with other particles. I then give every particle a random velocity within the range of -1 to 1. To color the particles according to their type, we can use the particle index to grab that particle's type and then use that particle's type to index into the dictionary. Finally, once the particles have been drawn, we can update their position by taking their current position and adding the velocity times delta time. So now if we run this, we should see a bunch of particles moving around on screen. But, well, that doesn't seem correct. Look, I'm not gonna lie to you, I actually did this on purpose. I think the mistake that led to this behavior could be used for creative purposes later on in the code. Anyways, the fix is simple. At the start of every while loop, just zero out the matrix that contains the screen information. Once that's done, you should get a field of particles just moving around randomly. But that's really all it is. And much like me, after a bad night's sleep, you couldn't really consider this living. I'm not going to bore you with the math. of how to make this interesting. There are much better videos explaining it than I could ever. But the basic idea of particle life that is applicable is that interactions happen within a radius, and the interaction forces for the particles are a piecewise function with a strongly negative piece of the function to avoid clumping for small distances, and for any distance above that, a symmetrical force function for attraction or repulsion that leads to interesting interactions. These final additions are the longest one, but do not despair. It's the home stretch, and once this is implemented, basic particle life will be working. The first thing I do is create a force matrix. This describes how every particle type interacts with every other particle type. Next, an interaction radius and a friction factor. This is to stop particles from gaining infinite energy, as asymmetric interactions can cause them to just zoom out of the screen. After that, I create the force calculation function for calculating forces between two particle types. Inside that, I define a minimum distance, and if the two particles are within that distance, I return the negative portion of the piecewise function. And if the particles are between that minimum distance and a distance of 1, then I return the asymmetric portion of the piecewise function. If the distance is greater than 1, I just return 0. Inside the while loop, I'm going to loop over every particle and set the forces acting on it to 0. Then I'm going to loop over every particle again. And if the particle from the first loop is different from the particle of the second loop, I calculate the difference between their x and y position. I then use those differences to calculate the Euclidean distance between the two particles. Next, if that distance is less than the interaction radius, I use the calculate force function to calculate the forces acting on that particle and add those forces to the total forces acting on the particle. After that, I scale the forces so that we can actually see some movement. Apply the friction factor to slow down the particles that have gained too much speed, and update the particle's velocity using the forces and delta time. Once again, the particle positions are updating using the particle's velocity and delta time. And the results are majestic. Particle life. What a beauty. However, there is one last problem I would like to solve, which is the fact that the particles tend to go off screen and never come back. Eventually, the simulation just looks kind of empty, and we're back to a deep dark void. To solve this, I'm going to make the boundaries toroidal, which is just to say that if the particles go off one of the sides, they just come back from the other one. The solution is simple. Just check if the differences in the x and y coordinates are larger than half the screen size. And if so, modify the distance in x and y so that the vector of the two points in the opposite direction. Finally, when calculating the particle's position, we just take the modulus with respect to the x and y size of the screen, so that when they go above those values, they just loop back around. And that's effectively it. You should have a fully functional particle life simulator. We can now play around with the simulation. If we remove the refreshing of the screen at every iteration, we get this interesting mom's spaghetti generator. I think it's quite pretty, but there are more interesting things we can do with it. If instead of fully clearing the screen, we just subtract a portion of the pixel values at every time step, you get this sort of fading tail effect. Honestly, I could watch this all day. Programmers tend to come down with a common ailment called a need for speed. And if you do feel so inclined to waste most of your free time in trying to get this to run 30% faster, then there are some improvements you can make. Primarily, spatial hashing to reduce the number of particles you have to loop through for every other particle, and pivot tables to rearrange the particles in memory to preserve cache locality.
Bonus round.
As a bonus, there's also a third method. The previous methods were effectively trying to make the computation smarter so that you have to do less work and thus it can run faster. But you could also take a sneaky third approach, which is just to do dumber, faster work. I am not going to go over the code, but on screen what you're seeing right now is a rewrite of the particle life to use matrix computations on the GPU. Just pause the video if you want to copy the code. It is again by no means the fastest GPU rewrite, but by using matrix multiplications, we can speed up the simulation to run about 10 times more particles. Well, that's it for today. If you've enjoyed this or it helped you in any way, please consider liking and subscribing. And until next time.